When it comes to computing decision values, it's obviously a little bit simplistic to only consider one side of the coin, namely how subjective value comes about in the domain of gains or rewards, which is what we've done up until this point. So let's consider also how costs and benefits are integrated into the decision values. And there's this one wonderful study by Croxon et al. That I just want to discuss really briefly. So what they did in this study is they had an effort task which could lead to different amounts of rewards. So that's a high reward and a low reward trial. And in the effort task, participants basically had to cancel out these kinds of targets by moving a cursor. And this could be anywhere between 3 and 20 targets, right? So you move a cursor, and once the cursor reaches this target, you cancel it out, and you have to do this repeatedly. So it's basically what behavioral economists call a real effort task. It's an annoying task that allows you to earn money. And in this experiment, the amount of money earned per cancelled target is 25p in the high, so pence. This is in terms of pounds, UK pounds or British pounds. In the high reward condition and in the low reward condition, it was 5 pence, so much less than that. And then we had different levels, or the experimenters used different levels of effort, namely low effort and high effort. And within each condition, 2 different levels again. So you could, in the low effort, the participants had to cancel 3 targets or 4 targets, and in the high effort conditions, 15 or 20 targets. And this was indicated to participants during the queue periods at the very beginning of such a trial. So let's go through these different cues, which participants actually learned implicitly. So we have the high reward, which is indicated by the horizontal bar at the top, and the low reward, which is indicated by the horizontal bar at the bottom. Right? This is how the queue tells you how much money you're going to win. Then we have the low effort bars, which are these vertical bars going down here on the left and on the right, where on the right indicates that it's a high effort type trial. So you have to cancel a lot of these targets to make the money that you can gain there. And this leads to a net value where reward is relative to the effort, which is something that the authors actually use later in their experiments. So participants see this queue, and this is actually the period that we're interested in. So during this queue period, can they make an accurate assessment of how effortful and valuable or beneficial this upcoming task will be? And then they learn how much money they've made during this task in the end. So we have the timeline here going down of the fMRI experiment. But we're mostly interested in the queue periods because that gives us an indication of the brain's predictions of the costs involved, which is the effort on the scale from 3 to 20 here, and the benefits involved, which is the reward, which could either be 25p or 5p. You might note that what's interesting, so here's an explanation of the queue again in color, which might be nice, but basically as the horizontal line goes up, that means high reward. As it goes as the vertical line goes to the right, that means high effort. And when we look at the behavior and the response times are used here as a behavioral dependent variable, we can see that when the conflict was lowest, so in high reward, low effort trials, reaction times were also fastest, right? These are trials that are actually quite beneficial. So the reaction time is measured here when they just have to push a button. So indicating basically that participants can identify these types of trials, high reward, low effort, meaning these are good trials for them. They're excited, so they respond a little bit faster. Now, the interesting question about this paper is how does the brain respond to this? And what they're finding is, just to give you a preview, there is a set of regions in the brain, which I'm showing here in yellow. They compute a net value. So that's the integration of the costs and benefits. And I'll go over these figures in a second. Then we have green regions, which respond primarily to the rewarding aspects. So they distinguish between high reward and low reward. And then the blue regions, so the green regions are in striatum and in insula, and the blue regions are in the putamen. They seem to distinguish only between the effort costs, which in the putamen makes sense because it's part of the motor regions within the brain. And we've learned about the striatum and the insula being also involved in valuation. But let's have a look at how the bold response looks like. So this is the net value regions here. And these are the stimulus. The bold response here is time locked to the time when the stimulus, the cue, is presented here, right? So the information about the value and the cost within this trial is available to participants. And across multiple repetitions, you can time log this and then average across these responses, and you get a bold response for each of these different conditions here. And the net value regions show this interactive effect. So they show that the highest value is given to low effort, high reward. So that's the highest bold response trials, right? Then the second highest is to high effort, high reward. That's the second highest bold response. Then we have high effort, low reward, and low effort, low reward. And here maybe the striatum follows a better response, because the ordering here is closer to the correct ordering. So you have high effort, low reward, low effort, high reward, high effort, high reward, high effort, low reward, and low effort, low reward. So that's the exact ordering that we would get if we integrate costs and benefits, right? Here, this is basically a good cost-benefit ratio, and here this cost-benefit ratio becomes bad. And you can see what the different lines mean here that are represented here as the bold response. So these are regions that integrate this value because they show an interaction between the two values, or between rewards and effort. Now let's look at regions that only represent effort. And there's this region here in the dorsal anterior singular cortex, which is basically showing a distinction only at the level of effort. They do not distinguish between high reward and low reward. You can see this basically by the fact that these lines do overlap here. So we have the low effort trials in the high reward and the low effort trials in the low reward condition, showing a larger bold response than the high effort trials in the high reward and the high effort trials in the low reward condition. So we have low effort up showing larger response because the costs are lower, and high effort trials showing a lower bold response because the costs are higher. So this is computing the effort costs in a sense, right? Similarly here in this figure. But this is reflecting the dorsal anterior singular cortex here. Finally, we have regions that respond primarily to reward, and this is in this region of the ventral striatum. And what you can see here is that we have high reward regions, no matter what the effort is, leading to a larger signal increase relative to low reward trials, no matter what the effort amount was. And a similar effect was observed then in this type of graph. But this is the ventral striatum that shows this exact activation pattern here. So based on these activation patterns, we can say that what the brain seems to do, it seems to have some regions that are involved in processing rewards, other regions that are involved in processing the efforts, and then a whole set of regions that are involved in integrating these two different pieces of evidence, right? So obviously, if we have costs and benefits that are processed in different brain regions, we have to have an integration aspect that allows us then to make decisions properly based on both the costs and the benefits, to assign a value to our actions and make a decision among, let's say, different choice options that offer differences in costs and benefits. So the interesting part is there seem to be regions involved in processing rewards and efforts, and regions that integrate this information and show an interactive effect. So the previous study has shown us how costs and benefits are integrated in the human brain, but there's actually a lot of work on this in the animal literature, and this is an example of an actually really excellent review by Salomon, Correa, and Farah and Mingote, published in 2007. And basically what they're showing here is one of these paradigms that's commonly used in the animal literature. And we have these operant chambers, which you may be familiar with. They're part of any kind of instrumental conditioning paradigm that's used with animals, with rats in particularly. And they're also called Skinner boxes. So what we have here is a lever that the animal can press to receive a highly valued food reward. So this is something that the rats really like. But they also get free access to this lab chow here. So a control rat that's introduced to this environment will start pressing. Let's say one press gives you one highly valued food pellet, and will not eat the sort of not so valued lab chow that the animal eats every day anyway. So there is a higher value here, and for this the animal will put in some work. And we can also increase the amount of work that's required, right, to get this food pellet. So we can say, well, actually, now that you know how this works, Oscar the rat, please you press 5 times before you get the food pellet. So then the work amount increases, and a control rat, so a normal rat, will still continue to press 5 times the lever to get one little food pellet, and then become satiated using this kind of food rather than eating the freely available lab chow. Now, the good thing about this is you can easily increase the amount of work that's required. So you can have a fixed ratio schedule of reinforcement, which means you have to press a fixed number of times the lever before you get the outcome, right? Before you get the highly valued food reward. And so we can increase this to, let's say, 20 presses, 30 presses, or even 100 presses. And a control rat will still be willing to put a lot of effort into getting this highly valued reward over the low valued reward. Now, when we look at dopamine depleted rats, and there's multiple ways we can delete dopamine. So one way would be by giving a dopaminergic antagonist such as haloperidol systemically. So you give an injection and then see how this rat's behavior changes. You can also delete dopamine directly within the nucleus accumbens, for instance, so in dopaminergic neurons, by giving injections directly into this region, which will lead to then dopaminergic depletions there. So let's have a look at how this dopamine depleted rat performs this task of a fixed ratio schedule with increasing amounts of work or effort required to get the highly valued reward relative to a control rat. And that's basically shown here. So these are the effects of dopamine depletion. And on the y-axis, we're plotting the amount of lever presses within 30 minutes. So the rat is in this environment, knows that it has to press a certain amount of times the lever to get the highly valued food reward, rather than just doing nothing and just eating freely from the lab chow, it's called. So here on the x-axis, we have the ratio requirement. And that means how many presses the rat has to make before it gets one pellet. So when we have just one press, so that's a very low effort type task, then the controlled animal does not differ from the DA depleted animal, right? But when we increase the ratio requirement from 1 to 4, from 4 to 16, and from 16 to 64, we can see that a vehicle control animal will ramp up its presses to receive the highly valued reward, and will work relatively hard and perform 2,500 presses in 30 minutes, which is quite a lot, right? Whereas a depleted rat will not do so. So it'll go up a little bit, but then at some point, this is just too much for the rat, and she will go down again, especially when it becomes 64, then this is just too much effort. You can see that this animal here is not willing, or on average, animals that show dopamine depletions in the nucleus accumbens are not willing to put in the effort. So another type of cost can be losses, and we talked about this in about a previous study, for instance, this one by Sabrina Tom here, and the one by Brooks et al. And when it comes to losses, we also have a cost-benefit assessment that participants are making in these types of experiments. So we have a gain value and a loss value. And also in these types of studies, we have seen that the potential losses and the potential gains, right? So the benefits and the costs are integrated in ventral striatum. So the largest amount of overlap is in the ventral striatum. And the same thing occurs also in the domain of pure losses. So when we talk about making decisions about more or less shocks, so more is obviously a cost and less is a benefit. When we weigh the costs and benefits in the domain of just purely losses, then we also see that the ventral striatum seems to integrate costs and benefits. So we can see that from work that's not looking at actual effort, but other types of costs and benefits, namely appetitive and aversive value, we see the same regions that seem to integrate costs and benefits. Now this opens a question, however, because we see that both positive and negative effects are processed in the ventral striatum. So this might be an integrative region in a sense, but it does deviate from what psychological theory predicts, namely that there are separate approach and avoidance systems. And in fact, there's also evidence for these types of approach and avoidance systems within the brain. So approach systems basically processing positive value, and avoidance systems basically processing negative value and emotions. So that's an open question that we can discuss further later.